Our research question was, how can we model the spread of misinformation with a three-state model where individuals are infected with misinformation, vaccinated for misinformation, or susceptible to misinformation? Primarily in this context, vaccinated means that you can't be infected with misinformation and you can save susceptible individuals from being misinformed by infected individuals. For this model, we split it up into two different methodologies. We had a simple methodology and a complex methodology. I'll be talking about the simple one. For the simple one, we basically counted the number of blocks in a von Neumann neighborhood around the center that we were looking at. And if the number of infected individuals are higher than the number of vaccinated individuals, then the susceptible center will become infected. We also implemented a randomness parameter where a vaccinated individual center can be randomly infected and not by proximity.
Now I will be talking about our complex methodology. We continued with the von Neumann neighborhood but implemented 19 different rule sets as seen here. However, there are more than 19 ways our rules can be implemented. For example, when looking at this rule, the vaccinated and infected neighbors can actually be in any location. As long as there are two of each, then this specific rule will be carried out. This was possible through using a state dictionary within our neighbors list and focusing on counts of each neighbor state, since the location does not play a factor in this model. As you can see, each rule also does not have exactly one outcome, as seen by these different split boxes here. This is because we included an alpha variable to represent how likely someone is to stray from the truth into believing misinformation. Within the rules, the alpha value is used to determine what outcome is selected through mathematical transformations. In terms of assumptions, we assume that the true information will eventually spread, so there is some weight included in the model to account for that. We also assume that the individual will not change state unless they have two or more influences as seen here. This cell is vaccinated and during this first 3 time steps only has susceptible neighbors, thus it does not change state. However, in this 4th time step, one of its neighbors becomes infected, meaning that in the next time step there is a possibility for change. This carries into our final assumption. Our final assumption being that when presented with both information and misinformation, a person will not simply jump from vaccinated to infected or vice versa. Instead, they will re-enter the susceptible state where their surroundings then impact their decision on what to believe. This is depicted by this cell here, where it begins as a vaccinated individual. However, its neighbors change and are infected, causing it to then turn to susceptible and then finally turn into infected. And that is an overview of our complex methodology.
Cierra and Chris talked about the 2 different rule sets we use to model our research question. Our complex rules are shown in the top panel and our simple rules on the bottom. On the left, we have the initial conditions of the matrix at time step 0. We take another snapshot at time step 5 in the middle and at time step 100 on the right. We can see that our complex rules start to stabilize towards vaccinated in the population by time step 5 in this situation. On the bottom, we see infected start to dominate even at time step 5. Where the 2 rule sets really differ is as we look at snapshots beyond time step 5. The complex rules allow the model to keep changing dynamically regardless of how far we look. The simple rule set, however, always converges towards everyone in the population becoming infected. As we look at the next couple of slides, we'll be able to see how these 2 models differ when we vary the parameters for susceptible, infected, and vaccinated. Focusing on just our complex rules, we can see that it is a lot more dynamic than our simple rule set. We can vary the parameters in a way that allow us to model clusters in the population that can either form, grow, merge, collapse, or ultimately, it allows us the flexibility to model the research question in a way that is more helpful than our simple rule set could. Here are a few more snapshots using our complex rule set and varying the parameters for susceptible, infected, and vaccinated.